Hello everyone. I am here to continue my previous lecture, which was on basics of drawing a Bode plot and understanding the concepts of Bode plot. In my present lecture, we will study frequency domain analysis specifically for the Bode plot, and we will study the procedure. What is the procedure to draw the Bode plot? Now we can see that first of all we have to take the transfer function, and in the transfer function we have to make the first most substitution as sigma equals s equals to j omega. So for the entire Bode plot we will study that sigma will always be equal to 0. So we are doing s equals to j omega in the open loop transfer function. Then we will find out the corner frequencies. Now what are the corner frequencies? Corner frequencies, let's say we have a system. Here we have GS HS equals to S by 10 plus 1 upon S by 5 plus 1. So here we have the first corner frequency, which is 5 radians, and then we have another corner frequency which we will be calling as omega C2, and it will be 10. So we can understand that this is due to a pole and this is due to a 0. So the first thing is we have to identify the corner frequencies. Now we are required one semi-log paper, and we choose a frequency range such that the plot should start with a frequency which is lower than the lowest cutoff frequency. So let's say we are the lowest cutoff frequency is 5 and then is 10. So to include 5 and 10 we must start with 1, and then we just mark angular frequencies on the x-axis and we make slopes, and on the left hand side of the y-axis marking the 0 slopes in the middle, and on the right hand side we mark phase angles by taking minus 180 degree. What they are trying to tell, that let this be a Bode plot. So this will be 0 dBs, and here we will be having minus 180 degree. And of course on this left hand side we will have magnitude plot, on this right hand side we have phase plot. Then we will calculate the gain factor and the type of order. Gain factor is nothing but, let's say in this transfer function we have a gain which is k, and that is 50 here. So gain factor is 20 log k. So here I have this k as 50. So 20 log k is nothing but 20 log 50. And then we have to see that what is the type of the of order of the system. And if we have these many requisites, we can calculate the slope and corresponding to each factor. Now let's say here we are going to discuss the determination of gain margin and phase margin. So for a beginner we just make the two curves as separate. Like here we have this portion is just the magnitude plot and this portion is just the phase plot. And what we are actually trying to figure out is, let's say this is a gain plot and this is a phase plot. We are going to plot the point at which the gain plot is crossing the 0 dB frequency, 0 dB axis. So we call it omega g. Now next we have to see the point at which the phase angle crosses minus 180 degree. So we call it omega p. So when we talk about here this is omega g, and here this one is omega p. Now here the two systems are slightly different. We can see that omega g is less than omega p, and here omega g is greater than omega p. And in this question we can see that omega g is less than omega p. Now there is few things ahead of this which we have to discuss. Now what we are going to see here, we are seeing that now from here we have to see that we have to draw few perpendiculars. what we are actually trying to do, we are dropping a perpendicular from omega p to the gain plot. Okay, now from 0 dB to this intersection, this will define me the gain margin. Similarly, what I'll do, I'll drop a perpendicular from omega g to the phase plot. Now this distance will give me the phase margin. Now here I see that the phase margin is positive phase margin, and here also the gain margin is positive. Why am I calling this gain margin is positive and the phase margin is positive? Why? Because here we can see that it is a minus 180 degree scale, and when we will mathematically calculate phase at omega equals to omega g, it will be positive numerically, it will be positive mathematically. When we will calculate gain like magnitude, 20 log of magnitude at omega equals to omega p, then that particular value of gain in decibels will be a positive value. Numerically that will be positive. We call it a stable system. So altogether this one is a stable system, and just by seeing the figure we can say that this is stable because omega g is less than omega p. Coming on to here, we can see we are dropping again a perpendicular from omega g till the phi equals to 0, and then we see that here we can see that this is the point where we can get the intersection, and we can see that this is a negative phase margin. From omega p we drop a perpendicular on the gain plot, and we see that this is again a negative value of gain margin. So for a system to be stable, the gain margin and phase margin should be positive, or we can say that omega g should be less than omega p. Now, stability conditions are given below. For a stable system, both the margins should be positive or phase margin should be greater than gain margin. Now, for marginally stable system, omega g should be equal to omega p, and both the margins should be 0, or phase margin should be equal to gain margin. Now, for unstable system, or if any of the negative or phase margin should be less than the gain margin. So this is the basic stability condition. Now in this numerical, we can see that we have this S. S represents pole at origin. Now from here we can see that first corner frequency is 1 by 0.4. So it is like S upon, we can write it as S upon 0.25. So the corner frequency is 2.5. Now another is 1 upon 0.1. So another corner frequency is 10. So we have to start with a frequency which is less than 2.5. So we are good to start with 1. Now since the system is type 1 system, type 1 system signifies that the initial line will have a minus 20 dB per decade fall. Now we are seeing that this term will is giving us no corner frequencies, but it is telling us that initial line will start at minus 20 dB per decade. Now when you will hit the next corner frequency, which is 0.25. Now this 0.25 is due to a pole. This one is a pole. So pole will add again minus 20 to the previous slope. So minus 20, this one, again minus 20, this one, total it becomes minus 40. Now at the next corner frequency, that is again due to a pole, we will add one more minus 20, and this is minus 60. Now we are good to go ahead with the plot, and we can start with angle information now. Here we can see that putting the different values of omega, here we can see that we are putting the different values of omega, and we are getting like 20 log 10 by j omega. So for this we are putting the value of omega as 0.1. So for 0.1 we are getting it as 40 dB. Yes, for omega equals to 2.5 we are getting it as 12 dB. Now for omega equals to next corner frequency, we have to see that at this point of time we have to add one more pole, so it will be minus 40, and for the next one it will be minus 60. So for first corner frequency, after the first corner frequency it should be minus 40, after the second corner frequency it should be minus 60. Coming on to the angular information. So angular information, the transfer function was 1 upon s into 1 plus 0.4s, 1 plus 0.4s into 1 plus 0.1s. So this will give a phase of minus 90. Again, this will give tan inverse imaginary by real. So imaginary is minus 0.4, real is 1. Again tan inverse imaginary by real, imaginary is 0.1 and real is 1. So this is the overall angle, and we will take different values of omega between the corner frequencies which we have included, like from 1 to the next corner frequency. We should include these two at least. So from 2.5 to 10 we should have. Now we are extending a bit. We are going from 1 or 0.1 till 100. So here we are going from 0.1 to 20. So for different values we have calculated, and here this is the required theta. Now we can see that here we have a Bode plot. In this Bode plot, at omega equals to 1, the gain was, and here is the omega value which is 1, and here is the omega equals to 0.1. So 0.1 we had 40 dBs. We can see here at 0.1 we had 40 dBs. So we started from 40 dBs, and at 40 dB we started with minus 20 dB per decade, and it will extend, it will go on extending till the point next corner frequency is achieved. Next corner frequency is 2.5. So we will max this 2.5 and this minus 20 dB. Now we'll stop here, and we will see the effect of this 2.5. This 2.5 is due to a pole. We will again add, this was minus 20, now we will again add one more minus 20, this becomes minus 40. And this minus 40 will come and stop at the next corner frequency, and the next corner frequency is 10. 10 is due to a pole, again minus 20. So this was initially minus 40, and again I am adding minus 20, it becomes minus 60. And this minus 60 will go on till the infinite, because we don't have any information further on this. Next, this is the magnitude plot. The phase plot is from 0.1 to 20 degrees. We have taken many frequencies. Now we can see that let's go for omega equals to, let's see that where the magnitude plot, here we can see that the magnitude plot is crossing, the 0 dB axis here. So this is omega g, and we can see that the phase plot will be crossing 180 degree. In this curve we can see that we don't have any, we will be having, let's say omega g is here, and minus 60 is here, minus 70, minus 80, and minus 180 will be somewhere down the line. So let's say this curve reaches minus 180 at any value which is after 20, after omega equals to 20. So after omega equals to 20, let's say it will be more than 20. Omega g is somewhere 5. So omega g is less than omega p. So omega g is less than omega p. We can see omega g is less than omega p, it is a case of a stable system. Now we will have for just 1 second we'll have a look on normal Bode plot. Here we can see that it is 1 and then it is 10 and I'm making it 100, and next will be 10 raised to the power 3, next will be 10 raised to the power 4. Let's say we would start from we can start it from 0.1. This will be 1 in that case, this will be 10 and this will be 10 square and then this will be 10 cube in that case. So this is how we advance on a Bode plot. Here the intervals are not uniform along the x-axis. We can see the widest interval is between 1 to 2 and the minimal interval is between 9 and 8. So this was a Bode plot, and we can predict the stability using the Bode plot with the help of gain margin and phase margin. Thank you so much.